All right, so now I'm recording. This is related rates 3.9. Fun stuff. Fun stuff. So with related rates, really it's about delving into doing some example problems. So that's what I'm going to do. And what we need to understand about these problems, when at all possible, try to draw diagrams so that you can best understand what's happening in the problems, right? This first problem doesn't lend itself very well to that because it's talking about how a balloon is going to expand. But you can look at that, right? You can see, all right, as you put air in a balloon, what it's doing is it's expanding this way, right? So we can see that the volume is going to grow as something linear grows. As the radius grows, the volume has to grow, correct? So it's important that you can picture that. All right, so in this problem, let's see if we can see what's happening. So it says air is being pumped into a spherical balloon. So we're to assume that this is a circle, but it's a sphere, so that the volume increases at a rate of 100 cubic centimeters per second. Now, something important about that is that we need to understand what it means by the volume increasing at a rate. Now, derivatives, we remember, are rates of change, correct? Right? That's absolutely critical that we understand that derivatives are, in fact, rates of change. And since it's a rate of change, what this is telling me is that 100 centimeters cubed per second is a volume rate of change. Okay? So we need to think of it like this. dV dt is 100 cubic centimeters per second. It is a derivative. It's a derivative specifically to volume. Is that clear? Okay. Okay, the other thing, it says how fast is the radius of the balloon? So now we're talking about the radius of the balloon increasing when the diameter is 50. So we're told the diameter is 50 centimeters, right? And we're trying to find out what the radius is. So we know that the radius is going to be half of that. But what are we looking for in the problem? We're looking for how fast the radius is going to be changing, right? Really, I should highlight it this way so you guys can see it properly. It's how fast. So how fast is asking for what? It's asking for another rate of change, but it's asking for a specific rate of change, and that specific rate of change is the radius's rate of change. Does that make sense?
Yes.
Okay. So here comes the hard part. Do you guys know your formulas for volume of a sphere? Oh, snap. I didn't think you were going to go there, Montiel, right? Unfortunately, it's one that you've got to know. So the volume of a sphere is going to be 4/3 pi r cubed. Okay? Now, we have a couple things. We have a dV, we have an r. We're looking for, the thing that we're looking for in this problem is we're looking for dr dt, right? That's the question mark. That's the thing that we're going after, right? So in this problem then, this problem here then, we need to take the derivative of it with an implicit with respect to time, right? Volume is changing with respect to time. Radius is changing with respect to time. So because both of these are being derived with respect to time, we must differentiate them implicitly. Does that make sense? So my dV dt is the derivative of v, And then that's equal to 4/3 pi 3r squared, but then I need to multiply that by dr dt because of the chain rule, right? The outside function was a cube, and now we have to take the derivative of the inside function, which is the r, but r is implicit because it's with respect to time. Are we okay?
Mm-hmm.
This is absolutely critical. If you can't get this step right here and understand how to differentiate this implicitly, we're pretty stuck in the mud here. All right? So the step from the formula to the derivative is very, very, very important. All right? One of the things that you'll know too with these problems when we're talking about with respect to time, they're always going to be implicitly done because time is something that affects everything, right? So now we're going to use some of the information that we know. Do we know what dv dt is?
Yes.
100 centimeters cubed.
Yeah, it's 100, right? We'll take care of the units later. We know that's going to be 4 pi. Do we know what r is?
25 centimeters.
That's right. So we know that that's 25, and then we're going to square that. Now, if we would have used the units, and I'll show that just so you guys can see on the side, we'll see that we actually get the correct units. So sometimes it is advantageous to use the units because then you know that you're doing it right. And I'll show that to the side. So then from here, I'm going to divide by 4 and divide by 4 pi. So I'm going to get 25 over pi is 25 squared dr dt. 25 squared is, what is that? Is that 625? But I don't need to even do that because when I divide by the 25 squared, isn't that 125 going to cancel it out? So I'm going to see that I'm going to have dr dt is equal to 1 over 25 pi. Okay? And if I write that as a decimal, that's 0.0127 centimeters per second is my dr dt. Does that make sense? The radius moves in terms of centimeters in one dimension, right? So it should just be centimeters. Correct? So we know that our units are correct. Now, just so you guys can see it, I want to be able to show it over here, and I'll do it in a different color, just so you guys could see it. So this was 100 centimeters cubed per second is equal to 4 pi 25 centimeters squared dr dt. This is just so you guys can see the units. That would have become 25 centimeters cubed per second over pi is equal to, I'll just leave the 25 squared and go centimeters squared dr dt. So when I divide, I'd get centimeters per second over 25 pi, right? Is my dr dt. And what do we want it to be in? We want it to be centimeters per second, which is exactly what we have. So sometimes it is advantageous to do the work with the units to be able to confirm that you end up with the right units. Okay? I saw your question, Carol. So right here, in both of these, correct? I divided by 4 pi. So what's 100 divided by 4? It's 25, and then the pi comes down below. Did the same thing here. Dividing by the 4 pi, 100 divided by 4 is 25, and the pi stays down below. Make sense?
Professor, what'd you do to get 1 over 25 pi?
Here? And here?
Yeah.
Sure.
Yeah, right there.
Sure. I can show that. So when I went 25 pi was equal to that 25 squared dr dt, isn't that the same as going 25 over 25 squared pi is equal to dr dt?
Oh, okay.
And
yeah.
so power rule.
Oh, okay.
Does that make sense?
Yeah, it does.
Okay, cool.
Thank you.
Yep.
Oh, Professor, you got rid of the 3's on the second step. They just canceled out, right? Like, because there was a 4 over 3.
So right here, this is a 3 in the denominator, this is a 3 in the numerator. They're just going to go away. Yeah.
Okay.
Yeah. All right. May I erase this piece right here? Like, is that okay? I can put it.
Yeah, that's fine.
I can put it back if you need, but I just want to keep the work for you guys clean. Well, and since I'm recording it, you could rewatch if you needed. But I want that. I just want to leave it as clean as possible. All right. Any questions on this problem at all?
No.
We're okay?
Yep.
So it truly is about being able to interpret what the question is asking and then going from there. Okay? All right, let me go on to the next problem. And again, these notes are up, so you guys can copy them, and I will post up the completed notes for you guys today as well. Okay, so don't stress. Okay, so looking at this problem, it says a ladder 10 feet long rests against a vertical wall. So the red is my ladder, right? So my ladder is 10 feet long. So that tells me that this should be 10 feet long, right? Against a vertical wall. If the ladder slides away from the wall at a rate of 1 foot per second, so the blue we'll call, let's see, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So this is going to be 6 feet, but we also know, we'll call that x. We know that dx dt is going to be 1 foot per second because that's the rate of change that the ladder, the bottom of the ladder is sliding away from the wall. So it's growing in distance, not shrinking in distance. Does that make sense? So it should be a positive growth away. Okay, another thing to understand. The ladder is 10 feet long, right? As it falls, is the length of the ladder changing?
No.
No.
No, the length of the ladder is not changing, and so we'll call it Z. The rate of change of the ladder's length has a
What?
change of...
A las 12.
Here, let me mute you guys real quick. If you want to speak, go ahead and unmute, but yeah. Just, something's happening at noon. What is the rate of change then of the ladder? The length of the ladder.
Raising 0?
It should be 0. So it's having 0 feet per second change in terms of its length, correct? Now we have to do a little bit of math, okay? Because what we're looking for is how fast is the top of the ladder sliding down. So we're looking for, and I'll use black for this, we're looking for dy dt of this thing, correct? And since it's going to be falling down, what do you think that rate should be? Should it be positive or negative?
Negative?
Should be a negative because it's getting closer and closer to the ground, so the height is dropping in value, not growing in value. Does that make sense?
Yeah.
Okay. How can we find the height of the ladder when the bottom of the ladder is 6 feet away? What do you think?
Maybe they change an angle of that top angle, or that angle change.
Well, I mean, we could do it complicated with trigonometry, but what about the Pythagorean theorem?
Oh, yeah.
Yeah, Sharon said it. The Pythagorean theorem, right? So what we could do is say, okay, we know that x squared plus y squared is equal to z squared, correct? And we know x, that was 6 squared. We don't know y, but we do know z to be 10 squared. So we're going to get 36 plus y squared is equal to 100. Y squared is equal to 64. So y has to be that plus or minus 8. But since we're talking about it in terms of a distance, we're going to use the positive, right? So now we know that this should be 8 feet. Does that make sense? Are we good?
Yeah.
Okay. So now we have to set up our all-important equations. So in the previous equation, we needed to know what the volume of the sphere was. In a problem like this that deals with right triangles, a ladder up against a wall, what do you think the equation is that we should use? Think simple. Don't make it complicated. We don't want to go trigonometric. So, I mean, we could. That would suck, but we could. What we want to use here is the Pythagorean theorem. Okay? So, we're going to go back with that equation. 2x plus, x squared plus y squared is equal to z squared. And since we're taking the derivative with respect to time, all of these are differentiated with respect to time. So all of these will be implicitly differentiated, right? So we're going to end up with 2x dx dt plus 2y dy dt is equal to 2z dz dt. Now, we can easily cancel one thing out, right? Everyone can see that the 2's can go. Right?
Correct.
Oftentimes when I do that, people are like confused, so I want to make sure that you guys are okay with that. And now we have all the information that we need. We're looking for how fast the ladder is falling. Right? So we know that the x distance was what?
X is dx dt.
So
X plus 6 feet.
the x should be the 6 feet, right? What is the rate of change with respect to time for x?
1%.
It's 1. What is our y in terms of height?
10. Oh no, it was 8.
It's 8. It's 8. We don't know dy dt. That's what we're going after. And z, the height of the ladder was?
10.
10. Very good. And what was the rate of change?
0.
0. So we can see we're going to get 6 plus 8 dy dt is equal to 0. So 8 dy dt is equal to a negative 6. Dy dt is equal to a negative 6 over 8. or a negative 3/4 feet per second. So at that moment, when the bottom of the ladder is 6 feet from the wall, the ladder will be falling at approximately, well, no, not approximately, exactly 3/4 of a foot per second. That's pretty fast. I would not want to be at the top of that ladder. Oh, the silence. I think so. What do you mean by that? You think people are confused?
No, it like cut out where you were like talking. Like I saw your mouth moving, but like I didn't hear anything for like a brief period. I don't know if that's what he was talking about.
No, I like my the Zoom call just straight up cut out and just reconnected me. Like I don't even know why.
Oh, really? That's bizarre. For me, you guys sound fine. But part of the reason why I record it, and I record it externally from Zoom, is because there's potential for Zoom issues. So this is really recording me on my computer, so there's no glitches. So when I post it online, you guys don't have those glitches that if had I recorded with Zoom. That's why I use an external recorder. So what did you miss?
I think I'm fine. I only missed like 2 or 3 seconds. I was just kind of like wondering if it was only happening with me.
Okay, okay, the 0, perfect. So that's easy. So think of it this way. Oh, you get the 1. Okay, so the 1 comes from here, right? The 0 here is what has you a little bit confused. Carol? Okay, so the way we're thinking about this is the ladder, as it's moving down, right? This is fixed, right? The ladder's 10 feet in length. So as the ladder's top is falling, that means this part of the ladder has to slide out this way. Does that make sense? Okay, so at the 6-foot mark specifically, the ladder is falling away from the wall at 1 foot per second. So the rate of change of this distance is moving at 1 foot per second at that 6-foot mark. Now the ladder is a fixed length. So this red line stays that red line at 10 feet. As the ladder moves and comes down and moves out, the ladder itself is still 10 feet long. Correct. So the rate of change of the length of the ladder, since there is no change to its length, has to be 0. Okay, good. Good. Make sense? That's important. So whenever we're talking about distances that are fixed, their rate of change is nothing, right? There is no rate of change. Okay? All right. May I go on to the next example, or do you guys need a second to copy this down?
Good.
Okay, let's go to the next one then. This is typically kind of a hard problem for people. So as I talk about this problem, if there's questions or uncertainties about things, please be sure to ask. So what this problem says here is it says that a water tank has the shape of an inverted circular cone. So the very first thing that I want to do when I'm talking about an inverted circular cone is draw it. So I'm going to go, okay, inverted means it's upside down, and it's a circular cone. Okay? With a base of radius of 2 meters. So what it's telling me is that from the center to a side, that right there is going to be 2 meters in length. So my radius there is 2 meters in length, correct? Okay. The other thing it's telling me is that from there to there, we have a height of 4 meters. In fact, I should call this like a capital R, and I'll call this capital H, okay? I'm not going to label them, actually. Let me just leave it like that for you. Okay, if the water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the depth of the water is 3 meters. So I'm going to do this in a color. It's water. So let's say that this is the water, right? And it's going to be at a height of 3 meters. So let's say this is 3 meters. Okay? Water is being poured into this tank at a rate of 2 meters cubed per minute. What does that tell me? What is that? What rate is that?
Height.
Not quite height. Height is one-dimensional.
Volume at which the water hose is pumping the water in.
That's exactly what it is. It's volume. How do I know it's volume? Volume's three-dimensional. So by being able to understand the units, we know that we're talking about a volume here. If it's squared, we're talking about an area, right? If we're in a single dimension, then we're talking about either a length or a width. So that's important that you all understand that. This right here is a volume, so I'm going to have my dV dt is 2 meters cubed per minute. Understood?
Understood.
Okay. Now, one of the things that I'm going to do is I'm going to do a related ratio. So what I'm going to do is the big triangle, and you'll see the big triangle that I'm talking about right now, is from here to here, compared to my small triangle, which will be from here to here. Okay? I know the big ratios, 2 and 4, right? I don't know the small ones, so I'm going to call this R and H. That's why I didn't want to label them earlier. Because instead of talking about radius and height, I'm going to compare them in terms of triangles. Okay? So one of the things that I can do now is I can set up a ratio comparison, right? Because if they're similar triangles, we know similar triangles have similar ratios, right? So my R over H should be the same ratio as 2 over 4. Agreed? Okay, now the important thing to find out here and what we want to substitute for matters in the question that we're being asked to find. The problem is asking us, find the rate at which the water level is rising. The water level rising. So if the water level is rising, are we talking about a radius or are we talking about a height?
Height.
We're talking about a height. So we want to substitute out r when we go to solve our equation. So that means that this ratio should be solved for r, because we're going to use it to substitute when we come up with our equation. Okay? Does that make sense to everyone?
Yeah.
Okay. Now becomes the important piece again. What is the volume of a circular cone? Oh, dang. People were like, sir. That was geometry. I had that like in 8th grade. Not me. I had it when I was older. I was not very good at math until I was older. But here it is. I'll give it to you guys. And then I'll explain to you how we get it. So the volume is equal to 1/3 pi r squared h. What ends up happening is the way that this was actually discovered, which is pretty cool. The Egyptians would have cylinders, and then they'd put cones inside of them and fill them with sand, and then compare the volumes. And they saw that it was 1/3 of a cylinder's volume. Isn't that cool?
Yeah.
So basically what ends up happening is you have a stack of circles. Like, you guys are probably old enough to still remember CDs. CDs stacked up, you'd buy them and they'd have those stacks of them, right?
Wait.
Huh?
Baby toys?
No, CDs, like CD discs.
Oh, yeah.
Like if you stacked them, right, you had like the stack of CDs so that you could burn your own CDs and do all that stuff, right?
Yeah.
That's my era, right? We would burn CDs and stuff. But it's a cylinder, right? Each disc is like a single circle. So pi r squared. And then the height is what gives you the cylinder's volume. Well, when you cut it into a cone, you're cutting out 2/3 of the cylinder. That's how they did it. Isn't that cool? But really,
Yeah.
it's just a stack of circles. Or some of you might know it like I did as a kid too. My mom would always buy this stack of tortillas. Each tortilla is a single circle, but if you stack them, what do they form? A cylinder. So that's the way I always think of how they come up with these equations. They just stack circles. This is the circle piece, and this is how high the circle goes up. How many circles it takes to get up to a height. Okay, sorry to go off on that tangent. I just think it's cool how that was discovered. They used sand to do it, which is so cool. Yeah, that actually sounds good. Maybe I'll get a breakfast burrito for lunch. All right. So now we have to do the implicit to this. So when we do the implicit, actually, before I do the implicit, I told you I wanted to get rid of r, right? Because what we're looking for in this problem is we're looking for the rate of change of the height. So now I'm going to substitute what r is with that 1/2 h. Okay? So I'm going to go, all right, v is equal to 1/3 pi 1/2 h squared h. So that should give me 1/12 pi h cubed. Does everyone agree with that?
And that's just because 1/4 times 1/3.
Correct.
Like,
Yeah, correct.
okay, cool.
Are we okay with that? I mean, I could have done the product rule, but you can see with the product rule, it would have been so much more tedious. And then I would have had a dr dt, and I would have been like, oh my god, what's a dr dt? I mean, I could have done it, but it makes the problem much more complicated, and we don't want to go after that. Okay? I mean, I can show you at the end if you'd like, but let's keep it simple. Right? Okay. So then from here, I'm going to do the implicit. So I'm going to get dv dt is equal to 1/4 pi h squared dh dt.
And how did you get that?
Okay, so the thing that I'm taking the derivative of on the right-hand side is the h cubed, right? The power rule will give me 3h squared dh dt, right? But 3 over 12 becomes 1/4.
Oh, okay. That's all piece.
Yeah,
Okay.
so I did that all in one step. Does that make sense to everybody, or would you like me to show that step?
Show the step.
Okay. Sorry, I take for granted some stuff, so I appreciate that you guys are willing to be like, oh, heck no, sir, you need to show me that. It's actually a good thing. So that becomes 3h squared because of the power rule, right? But then in the chain or implicit, I have to take the derivative of h with respect to t, so I get dh dt. Okay? That will then give me dv dt is equal to 3 over 12 pi h squared dh dt, which then gets me dv dt is equal to 1/4 pi h squared dh dt. We all right?
Yes.
Does that clarify it for you? Okay, so now we can substitute values in. What do we know that dv dt is?
Uh, 2 meters cubed.
That's right. So I'm going to just use 2. We have 1/4 pi. Do we know what h is?
No,
Yes, we do.
I don't think so. Oh, L.
Or
We solve it from that r equals somehow h.
So this is sweet. I'm grateful that you guys are struggling with this because it's so good. When are they asking me to find the rate of the height change? At what water level?
3.
At 3.
3 meters.
So we're talking about not the cylinder, or I'm saying not the cone itself, but the water level. So we're talking about the height here in terms of water height. So our height here should be 3 squared. Does that make sense? Because the problem dictates to us, it's saying find the rate at which the water level is rising. When? When is the key word. When the water level is 3 meters deep. So it's asking us for a specific point in time. And that specific point in time is when the water is at a height of 3. Right? Because this dh dt here is the rate of change of the height of what?
the water.
The water. Because what would be the rate of change of our cylindrical cone?
0.
0. Perfect. He for sure gets it. The cone's height is fixed. It's not going to change. Right? The physical cone that has the water isn't going to change. The thing that is changing is the water. How high it's going. Does that make sense? Do you see how these problems are about interpreting what the heck the word problem is asking? So with these problems, it's going to be a lot of practice on interpretation. Okay? Okay, so then let's solve this. So I'm going to multiply by the 4 to get rid of it. So I'm going to get 8 is equal to 9 pi dt. So then 8 over 9 pi is the rate of change of the height of the water. We can write that as a decimal as 0.28 meters per minute.
So you multiplied both sides by 4 to get rid of the 1/4, and then 8, and then just 9 pi because it's squared.
Yeah.
Cool.
And then dividing by that, right?
Professor Mankiel, I was just going over the work and I realized I got lost where it's you go from 1/3 pi to 1/12 pi, please. Where you combine the h's, each third. I just got lost.
From here to here?
Yeah, from
This step to this
1/3
step.
pi to 12 pi.
Right here. Okay, no problem.
Correct. Yeah, that's them.
So look at this. What is this going to become when I square it?
Just h squared.
8 squared, but what about the 1/2?
Oh, that becomes a 1.
Well,
Well,
that
sorry,
becomes
no,
1, but
one
what about the
over
2? 1 over 4, right?
Oh, that's right.
Yeah, 1
Minus
over
1/3
4.
equals 1 over 12.
Yeah, so 1 over 4 times 1/3
Okay, yep.
is going to give me that 1/12. Does that make sense?
Yeah.
All right, so since you got stuck on that.
I did my math wrong. I thought it
No.
was 1/2.
No, don't trip. But just so you don't, get caught with that again, I would leave yourself a little note on the side saying, "Hey, this is how that happened." Okay, just because.
Yeah, I ended up getting stuck in those.
Oh yeah, look, calculus. The real truth about calculus, guys, is that calculus is pretty dang easy.
Yeah.
What eats us up is the stuff we take for granted. Oh, what's 1/2 squared times 1/3? Oh, I don't know. And it's like, what do you mean? But it's important. It's important for us to get caught on those things, right? How many times are the mistakes that we've made on calculus things been like 3 minus 5, 2? Oh, man. Right? Those are the things that are eating you up. It's not the calculus. Yeah.
Yeah.
Most of you guys can go from here to here, no problem. Right?
Yeah.
From this step to this step is not a problem. That's the calculus. The rest of it is, guess what?
Algebra.
Substitution, algebra, arithmetic. And guess what happens? Where do you think the bulk of the mistakes come from? Right here. It's typically not from here to here. It's all the stuff in the math that you take for granted. One thing I'll tell you about your class that I really appreciate, most of my classes are too proud to ask questions about simple things like, how did you go from that 1/3 to the 1/12? Or asking for clarification of, how did I get that 8? They're like, oh, I'll figure it out later. Well, guess what? How many of you guys go back and really look at my notes with intention and study them? Very few people. So if you don't get it during the time that I'm talking about it, you're probably not going to get it. Because I can speak for myself. When I was a college student, I'd take notes in class and I'd be like, cool. And then I'd go do my homework. And then I'd pull my notes out just to look and see, okay, what was the steps that he did that's similar to the problem I'm trying to do? but I didn't really try to understand every single step. And that hurt me. So better for you right now in class to be like, I want to get every step so that when you're doing your homework, you understand the steps already. You're not like, wait, what's that step that he just did there? Right? How many of you guys look at your textbook and it skips a step and you're like, what did they do?
Yeah, I noticed that a lot.
Oh, they do it all the time.
Yeah.
And so if you notice, when I do the examples that are straight out of the book, I'm much more deliberate about the steps that I show and talk about, because they're the steps that get most people. It's not the calculus. It's the stuff that the calculus book takes for granted that you already know. Okay? So I do appreciate that you guys, as a whole, as a group, you are so willing to ask questions. You know, Carol's always asking questions. Ray asks questions. Gerardo, you know, you guys are all asking questions, and it's great. I appreciate it. You know, Daniel does it. It's good. Okay. All right. Let me show another example. I think this might be my last example. It is. And then I'll go over some homework questions you guys might have. Okay. So we'll have a good chunk of time to be able to go over some homework questions. Okay. And then on Thursday, what we'll do is we'll do a little prep for the exam, and I'll do something with chapter 4, maybe one section in chapter 4, and then spend the rest of the time prepping for the exam. Okay?
Right.
The exam that we're gonna have. Okay. Here we go. Let's do this example.
Yeah, my Zoom cut out for a quick second, so I didn't hear like the back half of the sentence.
Oh, gotcha. Now, are the rest of you experiencing that as well?
No,
That
mine is
happened.
Are
That
you-
happened to me earlier, but I'm back on.
Oh, okay. Yeah, you know, I think part of it is sometimes the Zooms do get bogged down. I've actually been pretty fortunate. Mine's been all right, but, you know, some of that could just be Wi-Fi connections. I mean, at my house, right now, my television is on an Apple TV, and it's connected via Wi-Fi, and I can't get my TV to work. But my internet is on fire in my house. It's good. It's just, for some reason, my TV doesn't work. The cable TV doesn't work. So I gotta call and complain about that or something. But I mean, and you know, I mean, we're all paying for a bunch of internet now, and we're running into these issues. But oh well. Okay. So before we get into this problem, we need to talk about. I don't need TV. It's true. I really don't. I don't watch TV very much. It's really, to me, a waste of time. I read a lot. But my kids and my wife like to watch TV. Okay. Before we get into this problem, we should talk about some basic directions that you already know or should know, but I'll reinforce it for you. So this is going to be east, north, that's south, and this is west, so that you have the correct orientation when doing these problems, okay? So in this example here, it says two cars start moving in from the same point. So this is the point where they're starting. One travels south at 60 miles per hour. So let's call that dy dt, because we're talking about it in terms of y. So this will be the y direction, right? Because up and down on a paper, we typically think of it as y. And then it says the other vehicle, or the other travels west at 25 miles per hour. So we'll call that our dx dt, right? So this direction will be x. And it says at what rate, so they're looking for a rate, is the distance between the two cars increasing 2 hours later. So what we're looking for is we'll call this z. We're looking for our dz dt for this problem. Does that make sense how I set up my picture for this problem?
Yeah.
Okay. So cool. So it says 2 hours later. So in 2 hours, how far did the car going west travel? What do you guys think?
So the question is, so the y in 2 hours will be at 120 miles, and the other one at 50 miles in 2 hours?
That's right. So this one will be at 120 miles, and this one would be 50 miles, right? Does everyone understand how that was achieved? Okay, good. So now that we have that information, since we're going north, or we're going south and west, we know that we formed a right triangle, correct? Okay, just to make sure everyone can get this, if we're going 25 miles an hour consistently, after 1 hour, we go 25 miles, right? After 2, we would have gone 50 miles. After 3, we would have been at 75 miles, and so forth and so on. This rate times the amount of time will give me this x, right? Also, here, this rate times the amount of time will give me this. So if it's 60 miles per hour and it's 2 hours, I'm going to go 60 times 2, and that will give me my distance. All right? Just to make sure everyone gets it. So if I would have asked for this problem, it would have been 3 hours. You would have gotten 75 for x and 180 for y. Okay? All right. Now, since we know it's a right triangle, does everyone get that it's a right triangle?
Yes.
That's important, right? Because the north, east, south, west all form right angles, right? So south and east are right angles, south and west are right angles, west and north, right, and north and east are right angles to each other. So we know that this is a right angle. Since it's a right angle, we can find out what z is by using what?
Pythagorean Theorem?
There it is! Isn't that funny? That just came right back. So we know that we're going to have x squared plus y squared is equal to z squared. So we know that this is 50 squared plus 120 squared is equal to z squared. So that's going to be 2,500 plus 14,400 is equal to z squared. So z is equal to, what is that, 16,900. We're going to deal with it in terms of positive only because we're talking about distance. And that's going to be 130 miles. Right? So we now know that the distance between the two cars after 2 hours is 130 miles. Okay? And we should have known that, right? Because it's a 5, 12, 13 triangle. Right? You know your Pythagorean triples. You guys all have them memorized. I'm joking. I'm joking. Although you should know some of them, right? 3, 4, 5. 5, 12, 13. There's a bunch. Okay. So now that we have our x, our y, our z, we have dx dt, we have dy dt, we're looking for that dz dt. Now we have to set up our equation for the implicit differentiation, right? To be able to do our related rate. So what equation are we going to use? We're talking about a right triangle.
The Pythagorean theorem.
It's the Pythagorean theorem. So anytime we're dealing with a right triangle, we want to try to incorporate the Pythagorean theorem. Okay? So then let's do it. So then x squared plus y squared is equal to z squared. So we're going to get 2x dx dt plus 2y dy dt is equal to 2z dz dt, right? And what we're doing is we're trying to solve for that bad boy. Agreed? Okay, let's get rid of the 2's because we don't need them. What is my x distance? What was it? At the 2 hour mark, what was my x distance?
50.
50. What was my rate of change with respect to x? Or rate of change in the x direction?
25.
25. The y distance after 2 hours, I believe, was 120, right? And the rate of change there was it 50?
60.
60, I couldn't remember. 60. Okay. What is our z?
130.
130, and then what we're looking for, correct? All right. So 50 times 25 is 1250 plus, what is that, 7,200 is equal to 130 dz dt. And I should highlight these just so we are consistent. What is that going to be? 8450 is equal to 130 dz dt. And I think that comes out to be 65 miles per hour. So what this is telling me is that after 2 hours, the rate at which the cars are separating is 65 miles per hour at that instant. That's a lot. Are there any questions on this?
Nope.
Straightforward? Oh, till you do the problems.
Until we do the problem.
That's what I just said, right? Until we do the problems. All right. So that's all I have in terms of like lecture stuff for today. I don't want to overwhelm. So I want to answer some homework questions. May I stop recording and then just put up the notes, or do you want me to record the homework answers? Either way doesn't matter to me.
It doesn't hurt.
I'll just keep recording. It's fine. All right. What homework questions do you have?
Number 11. Number 11 and F count 7.
Okay, hold on. Let me get my WebAssign up, and then we'll do it.
That's the problem there. Held it up to the.
That's your problem? Okay, no.
Yeah. I don't know if I did the algebra right.
What number was that? On 7, right?
11, number 11.
All right, I'm popping it up right now. Hold on. All right, so they want the first derivative of this thing. All right, so this is 3.4, number 11. And what I have is y is equal to 6 sine of pi x. Okay?
Correct.
What, do you want me to do it with your number 11?
I don't know. That's fine. I think it's the same. It's the same thing. Because I don't know if I'm putting it right on the WebAssign and I'm not putting the right format, or.
Well, here, let's see it.
Wrong.
Okay, so I'll do it and see if you submit it like I do it. All right, so the first thing that I'm going to do is I'm going to take the natural log of both sides, right? So that's going to be ln is equal to sine pi x ln of 6, right? So then I'm going to get 1 over y dy dx is equal to cosine of pi x, right, times pi times ln of 6. Agreed?
Agreed.
If I take the derivative, if I did a product here, to take the derivative ln of 6, ln of 6 is a constant. It would have given me a 0. Right? So I've done the derivative on that side. So I'm going to get dy dx is equal to y times cosine pi x ln of 6, and then I'll put the pi in front. Agreed?
Agreed.
So then all I have to do now is substitute that y for what it originally was. In fact, I can make it cleaner. And there's your answer. So your answer, since you had 11s, would have been 11 and an 11. Does that make sense?
No, I found my mistake. Yeah, I found my mistake.
What was it?
Yeah, I noticed the first step you did. I didn't take the natural log of the y on the left hand side of the equation. I just took it on the right side. I'm like, oh, crap.
Got it. You got to do it to both sides, right? What you do to one side of an operation, you have to do it to the other. All right. All right. Any other questions?
Thank you. Hey, let me just copy that down.
Yeah, no problem. Any others? Oh, can you do number 18? Sure. All right, so here's number 18. I won't move it too much for you. This is on...
All right, I got it.
Okay. This is on 3.5, number 18. And it's find the derivative of tan of x minus y is equal to y over 6 plus x squared. Okay, so we want to find, they're asking us to find dy dx. Okay? So, I'm going to take the derivative of tangent, and the derivative of tangent is secant squared x minus y. And then the inside piece, the derivative of x is 1, minus the derivative of y is dy dx. And then on the other side, I need to do the quotient rule. So the derivative of y is dy dx times 6 plus x squared minus y times the derivative of 6 plus x squared is 2x all over the denominator squared. Are we okay? Okay. Now the goal is to get this guy together with this guy, right? So that's going to take some maneuvering. So what I'm going to do is I'm going to try and clean this up. So I'm going to get secant squared x minus y minus dy dx secant squared x minus y is equal to, I'm going to separate this thing over here. So I'm going to have 6 plus x squared over 6 plus x squared squared dy dx minus 2xy over 6 plus x squared squared. Are we okay with that? I'm not trying to skip steps so you guys can all see. I'll clean it up before I gather. This is going to be 1 over 6 plus x squared dy dx. And now I'm going to move things. So I'm going to get secant squared x minus y plus 2xy 6 plus x squared squared is equal to 1 over 6 plus x squared plus secant squared x minus y dy dx and shoot, do you guys want me to make it clean denominators? You want me to do the whole clean denominators thing? Or can you guys do that arithmetic yourselves? Let me know. Would you like me to do it?
Yes.
Sure.
Do the work. Thanks, guys. All right. So that's messed up, guys. Appreciate you. All right. So I'm going to go 6 plus x squared squared secant squared x minus y plus 2xy all over 6 plus x squared squared is equal to 1 plus 6 plus x squared secant squared x minus y all over 6 plus x squared dy dx. When I multiply by the reciprocal, this is going to cancel one of these. Agreed? Do you agree, or do I need to show it? Because
So I
this is going to flip when I bring it to the other side, right? To multiply?
Yes.
Okay, so then I'm going to get 6 plus x squared squared secant squared x minus y plus 2xy over, we have 6 plus x squared times 1 plus 6 plus x squared secant squared x minus y is dy dx. Well, that's funny. I can reduce just a little bit more, and I'm going to get 6 plus x squared times secant squared x minus y plus 2xy over 1 plus 6 plus x squared secant squared x minus y. And that is the answer. No big deal. Until it's a big deal. If we have to, you do. I guess that's true, right? If I want to teach well, I should too. All right, that was a lot of steps. Does that make sense? Does anyone need me to scroll up so you can see something on this problem? Or is it okay? Any questions?
Can you scroll up, please?
Can I what?
Can you scroll up, please?
Yeah.
Right there is fine.
Okay.
Thank you.
Yeah, I'll do that one in a second. All right. Let me know when you're ready. Okay. All right, so I guess the next one was number 35. Let me see what 35 is. Okay. This is in 3.6, number 35. It says y is equal to ln of x cosine of 12x. Okay. So here, I'm going to go ln of y of ln of x cosine of, oh, in fact, I don't even know if I need to do this. I think I might just be able to go straight into it. I'll just do it. I'll follow the pattern so I can drop it down. Okay, so then from here, I'm going to get ln of y is equal to cosine of 12x ln of x, correct? So what's going to happen is I'm going to get 1 over y dy dx is equal to negative sine of 12x times 12 times ln of x, right? But it's a product, so I'm going to get cosine of 12x. Ln is going to be 1 over ln of x, but then I need to multiply that by 1 over x. That's probably where people get caught, right? This ln gives me 1 over ln of x, correct? But by the chain rule, the derivative of ln of x gives me that 1 over x. Does that make sense? So, negative 12 sine of 12x ln of x plus cosine of 12x over x ln of x. And now I need to multiply by y. And I'll just rewrite it this way. But then we know what y is. Y was what? Ln of x to the cosine of 12x. Cosine of 12x over x ln of x minus 12 sine of 12x ln of x. Christmas. Aren't derivatives fun? I think the next one is number 8.
Correct.
Okay. Are we okay with this? Can I go on to the, they are so long. Yeah. But once you see the pattern and you get them, it's just writing. I don't know. I mean, you see, like it takes me what, a minute to do the problem. When you guys do it, it's like yeah. it they're long. Yeah, I don't know. It's like essays, right? It's mathematical essays. Okay, let me do number 8. So this is number 8, and it's from section 3.4, and it goes like this. Y is equal to a to the 4th plus cosine to the 4th x. Right? And so they're asking us to find dy dx. So a to the 4th, what's the derivative of a constant?
Constant is 0.
0. So a to the 4th is gone. And then we need to go change the power rule. So it's going to be 4 cosine cubed of x times cosine's on the inside, so negative sine of x, right? And then if we want to take the derivative of x, we know that that's going to be 1. So then we see that this is going to be a negative 4 cosine cubed x sine of x. This is more to your speed, Carol? Yeah.
And my mistake was that I didn't think of a as a constant.
Yeah, it's a
The
constant.
derivative of a. And,
Yeah. Yeah,
so
yeah.
letters that are in the beginning of the alphabet should be regarded as constant.
What's that? I'm sorry?
So if we see like a letter that's at the beginning of the alphabet, we regard them as constants.
Unless we're talking about it implicitly,
Uh-huh.
then you would take a derivative of it. But since this here was before I even talked about implicit, a is just a constant.
Okay.
All right. Any other questions?
I have a question. What does it mean, implicit and implicit? Like, how does that relate to? Because if it was x to the 4th, then we would have taken
4x cubed. Yeah, it would have been 4x cubed. But so implicit means when that variable is, and typically we don't use other letters, we'll use x and y and do the implicit differentiation. So let me see if I can find one for you that was done implicitly. I think I did a couple. Well, even here, right? So in this example here where I went x squared plus y squared is equal to z squared, all of those are being derived with respect to x because I couldn't isolate for one variable, right? So when I take the derivative of each one of those is understood to have some dependency on x, and so they must be done implicitly. This problem that we just did, we're treating a squared as the general a to the 4th as any number to the 4th plus cosine to the 4th x.
Oh, I see.
So if that would have been like 5 to the 4th, what's the derivative of 5 to the 4th? It's 0.
Oh, okay, I get it. Awesome. Okay, thank you.
Yeah, no problem. All right,
Professor, I have another question. It's
Sure.
still along the same lines with being able to identify constants as letters. So I wrote it down on this paper. I forgot which question it was. I don't know if you can...
Okay, so let me look at this. So you have g of x is equal to 2r ar of x plus n to the p.
Correct, huh?
Okay, so the only variable here, and the reason I know that it's the only variable, is it's g of x. So we're going to take the derivative with respect to x. Everything else is a dang constant. So in this problem, when I go to take the derivative of it, and this will come with experience, right? It takes some time, right? But since it's a function notation with respect to x, we're taking the derivative with respect to x. So g prime is going to be p times 2ra rx plus n to the p minus 1, right? Times 2r, and then ar to the x is going to be ln of a, or actually I should write it clearly. It's going to be arx ln of a times r. And the question you're probably going to ask is, how the heck did I get this?
Correct, yeah.
And that comes from something I gave you in class, which is a to the x, the derivative of a to the x, remember?
Yeah,
Is a to the x ln of a.
Nice.
But since there's a number in front here, the next step after doing the a to the x ln of a is to take the r to the x derivative by chain rule. So r to the x's derivative is r. You with me?
Yeah.
Okay. It's all a bunch of building blocks. I don't know what this problem was, but okay. Any others? How are you guys feeling?
Okay, not too bad.
You all right? All right. Well, scared, tired. Well, do you want me to like just stay on and answer questions, or should I stop recording and then I'll just stay on if people have questions and you guys can do work? I don't mind. You know, part of it is you guys got to put in your time doing your work, right? And then come in ready to answer or have me answer questions so that you can totally grasp it. Because if this is the first time you're seeing some of these problems, yeah, it's going to be rough. I got rid of the 8th assignment. Ray? Christmas, that's true. All right, here, I'll stop recording. I don't want this video to be like 12 hours long if I'm just sitting. So when you guys ask questions, I'll keep it on these notes so you guys can see them, okay?